departure function of the chemical potential component in a mixture. We saw that this can be written at a fixed temperature, pressure and mole fraction or mole numbers. Can be written first as an integral over the volume of the Z is the compressibility factor of the mixture. This is the formula. So given an equation sticker, main objective is to calculate this. So we took as an example van der Waals equation of state, which is given like this. So first is to express the equation of state in terms of the temperature, the total volume and the total mole numbers of each of the C species. So towards that I can write this as nRT. Let's say I multiply both sides by both numerator and denominator by n. This is actually a small d. So when I want to differentiate this with respect to ni, particular mole number, so I have to differentiate term by term. So the first term would give me RT by V minus N V mix times the derivative of N with respect to Ni, which would be 1. And then I have, we would then have plus RT, rather nRT times the derivative of this, which would be minus 1 over V minus N V mix whole square times the derivative of minus NP mixed with respect to Ni. So that minus sign would cancel with this. And then I have minus 1 over V square d by d Ni of N square A mix. So with respect to the mixing rules that we have chosen, right, which is that B mix is given by sum over j into 1 to C Bj Z A mix given by sum over I into 1 to C sum over j into 1 to C Aij. We showed yesterday that d by d in I of N B mix is simply di d by d in I. N square A mix is 2 times sum over j equal to 1 to C Aij in J. But now put everything together and calculate first this integral. So the integral would look like this. So integral can now be written as integral infinity to d. So I have RT by d prime minus n d mix. And then I also have a minus RT by d prime. The two, if you combine, so each by itself would lower if you calculate the integral. So when I combine the two, you would see that they can be easily shown to lead to a finite value. And then I have the integral of this, right? nRT V minus N V mix square, right? nRT times Vi by D minus N V mix square. And then I have minus 1 over V square times 2. So that would be minus 2 over, this is again prime, minus 2 over V prime square sum over j equal to 1 to C Aij Nj and D prime minus RT log Z. going on there? Parallel discussion, isn't it? Can you come forward here? We'll follow the route of the other students who dropped off the board. Nobody is forcing you to register for the course. Still opposite. Still maybe time to drop out of the course. To make my job easier. The date is gone. You have done it by yesterday. I can't help it now. So now this integration, infinity to b RT log would be e minus n b mix by b. That you can easily verify. This would be RT log b minus n b mix b minus the top limit, the bottom limit of infinity, the lower limit infinity would simply go to the order of 1, which would be 0. And then I have this would be plus 2 over b sum over j equal to 1 to c a I j n j, because minus 1 over b prime square would be 1 over b, and then again we would get only the upper limit, the lower limit would be 0. And any other terms that I have missed out? I missed out this term, so that would be right here. So this is giving rise to this. So this would be minus nRT bi. So I have plus b prime minus whatever square. So that would be minus 1 over b prime minus nb mix. And again, only the upper limit terms would come in. So I get b minus nb mix. And then I have minus RT of z. Now if you see this, because we started out converting it, this is actually the chemical, but this is the scope all the way here, so the matter of the equation A, that is the departure function. Now you can see that the dependence on B and N is somewhat illusory. You can easily convert it to a dependence on T, the specific volume and the mole fraction. For instance, I can simply C divide rho by N, and so I can make this RT log B minus B mix by B. And we know that B mix is a function of the composition. We recover that, the fact that this is an intensive variable effectively, and it can be expressed as a function of the intensive and specific variables. And then I have again plus 2 over b sum over j equal to 1 to c a I j z j, and then I have minus RT bi divided by b minus b mix, again dividing by n, and this is a function of RTPB, which is a function of P. So what the point here is that you are asked to calculate given temperature, pressure and mole fraction. The final answer is, can we do that? So the more numbers need not be specified. Even though we use the rule of expressing everything in terms of the total volume and the mole numbers, that only to simplify the calculation. So the whole thing will become quite messy to do if you are working in the specific ratio. So we converted it to that, right? And finally, can we calculate, right? You have to ask on specifying P, P and Z, can the departure function be calculated? Yes, it can, but I have to find B, which I can find by going to the equation of state. Once P, P and the mole fraction is given, then I can find B mix and A mix, and go and find the corresponding volume. Right? And then I'll get this. So I have the volume, the mole fraction, temperature, volume, and mole fraction, and the pressure. Now this has to be done by each and every component, right? So if you notice, so this is a property of the mixture. B mix is also a property of the mixture. The I comes in here, Aij. It will depend on which, the sum is only over J. The I stands out. That will depend on which component you choose among the C components. And then where is the I is coming? The I is also coming here. Everything else is an overall mixture property. And here we can clearly see that the departure function, so even the ith component is a function of all the mole fractions. Right? So it's a function of the overall composition of the mixture. It doesn't depend just on the particular component mole fraction. Now we can also express, I introduce the fugacity of a component. After the fugacity of a component in the mixture is P times Zi exponential of by RT. I can now introduce the fugacity coefficient.
Actually, this is negative dou P by dou T.
Oh, this is negative.
Yeah, and plus RT by dou.
Plus RT by dou. Maybe just check the formula. Yeah, you're right. Everything has a negative. So this will now become negative, right? And this will also become negative. And this, of course, now will become positive. That will no change in that. So let me rewrite this. So this will now be minus. Now we have it minus, and then plus, and then minus. Yeah, you're right. So this is an error here with the sign. So this is actually RT by D prime minus dV by D in I. So we've got the answer. Now we can go back to. So this is the fugacity of component in a mixture. Now I can define the fugacity coefficient as so this whole expression then becomes RT log phi I mix can be written because this is phi I by dzi. So phi I mix is actually simply exponential of just like the fugacity of the pure component. So this is the fugacity of a component in the mixture. So RT logarithm would give me the departure function. The departure function of the chemical potential evaluated the same temperature, pressure and mole fraction. And for the ideal gas mixture as for the mixture is RT log the fugacity coefficient, and there are obviously C such coefficients in a mixture. So now what I will give as an exercise is that I don't have all the answers, but you can go back to the earlier problem, ethylene and propylene. We consider this mixture problem. And this is component 1 and this is component 2, and we consider the case that Z1 was 0.7 and Z2 was 0.3. We also consider two states, T1 equal to 323 Kelvin and T1 equal to 10 bar, and then the second state 600 Kelvin and P2 was 60 bar. Change the notation slightly for the temperature pressure. I am now marking the different states by superscript rather than by subscript, so that you don't get confused with the component, which is now here coming as a subscript. Right. So now I will leave it as an exercise that you can type in 5I mix I equal to 1 to 2 for both states. So there are 2 states and 2 components. You can find out who the calculate. So there is another way in which this whole expression is written. If you see, the RT can be cancelled. So if you want to cancel RT, so I divide both by RT, right? So then it gives an expression for the logarithm of the fugacity coefficient dividing both by RT. So somebody can easily calculate the fugacity coefficient of the mixture. Now we have already given one of the crucial points is calculating the volume. If you recall, I already gave the volume to you, the specific volume. For the state 1 it was with this. Now you can easily, just a question of substituting and finding out. So you can just calculate the fugacity, see if you are able to calculate it. Now there is another way in which this is written in terms of the compressibility factor, right? So if I multiply both by P over RT, the numerator and denominator, I will get Z, and then I convert it to actually this minus log of 1 over Z, that is going to cancel with this. This is also Z, if you notice. So there is a minus log Z, right? There is also minus log Z here. There is a plus log Z. So this is log of Z minus B makes minus log Z. There is another minus sign. So that will cancel out. So you can actually remove. So maybe we can simplify this by simply dropping off this term altogether. So I have logarithm of Z minus B mix. Right? This I don't think we can do much. And then this can be written as RTBI by Z minus capital B mix. And that's it. So you have to gather this together. So and so I can now write the whole thing as, write it here, log 5I mix is logarithm of 1 over Z minus B mix. Now what is B mix and capital B mix and capital BI? Where the capital B mix is small b mix times P over RT. It will differ for the 2 states. And the BI is simply BI times P over RT. This is another standard way of writing. So always simplify the calculation. So log 1 over then I have the other term plus BI by Z minus B mix, and then minus 2 over P times RT, sum over A to 1 to C, A, I, J, Z, J. This is the mole fraction, the lowercase z. So are there any questions? I have cancelled out to check the sign. These formulas are available in the standard textbook for random course. You can go and double check that. So this is what we have actually is the carry of the numerical calculation and time play. So this will give another indication, because the z we have said gives an indication, the capital Z gives an indication of the deviation of the actual mixture from the ideal gas mixture. If Z is equal to 1, then you get the ideal gas mixture. The same way, the 5I mix, the clearly for the ideal gas mixture, Fi is equal to P times Zi, and so the fugacity coefficient will become 1 for each of the components in an ideal gas mixture by calculating the fugacity coefficient and comparing it to 1 for each of the fugacity coefficients of the 2 components. You can get some more idea how close is the behavior of the actual mixture to the ideal gas mixture. So that is what I have to say. Are there any questions on the calculation of fugacity coefficient from an equation of state? So the other equation of state, similar formulas must be available. You have the alpha also coming in for Craig Robinson. It is a function of temperature. But here there is no derivative with respect to temperature. In this formula there won't be too much of complication. You just have the A times alpha of T as it is. Right? It will be a function of temperature. So you have to calculate that for the temperature for mixture also. Are there any questions? Okay, if not, I will introduce another important ideal substance which is often referred to as an ideal solution. Right? So let me do that here. An ideal solution. I am not going to derive in detail the properties. The ideal solution, which is often used to model liquids, is defined like this: ideal solution, or abbreviated as IS. The ideal solution is one where each, this is also a mixture, is given by the chemical potential of each component in the ideal solution is given by pure component chemical potential plus RT logarithm of the mole fraction. We have to compare it to the formula for the ideal gas mixture, which is also a function of temperature and pressure. Only we use YI. Typically, the ideal solution is used as an approximation for liquid mixtures. Books tend to use XI here. If you want, I can do the same. It doesn't matter what I call it as. This is what it is. So the difference is clear. So the ideal, this term is the same. RT times the logarithm of the mole fraction. But this one, the ideal gas mixture, it would be the pure component ideal gas chemical potential. Here is the actual pure component chemical potential. That's what distinguishes an ideal solution from the ideal gas mixture. So the properties can be very easily, the partial molar property would be EI, which is now a function of T and P. EI, Pm would also be EI, but importantly now it's a function of both in general, temperature and pressure. HI, very similar to the partial molar property in the ideal gas mixture. Take everything was equal to the pure component ideal gas property, you will easily prove. I am not going to prove this. SI Pm is SI minus R logarithm xi, and similarly you can write the A and G. IPM is directly given by this, so I can write that also. And so on for I equal to 1 to 0. So the both pure the partial molar property of corresponding to the volume, internal energy and enthalpy is simply the pure component, a specific volume, specific internal energy, specific enthalpy. And similarly with the enthalpy, for the entropy you will get an additional term, volume minus R log xi. And similarly to the Gibbs free energy partial molar property. This can be very easily proved. So let me prove this. And similarly, now you will define here the mixture change in property on mixing is defined as with respect to, because there when we calculate change in property of the volume and total extensive property of the ideal gas mixture, the base was the ideal mixture, separate ideal gases. Here it would be simply defined as, for the ideal solution would be the U of any property minus sum over I equal to 1 to C psi ui. Then you will find that the change in volume of the ideal solution is also zero. Change in on mixing, change in volume of the internal energy is also zero. Of the enthalpy is zero, but for the entropy and Gibbs free energy won't be zero. That's again a definition, because for the ideal gas mixture, the change in property is with respect to the separate ideal gases. Here we simply define it like this to make them zero. Volume of the internal energy and enthalpy. So I'm not going to go into detail on this, but important also is the just as we have the fugacity coefficient, there is also another coefficient called the activity coefficient of a component in a mixture, which is defined as, this is now a general mixture, but it will be based on the ideal solution. Right? So this is now defined as exponential of, but the deviation is now from the departure is now from the ideal solution by RT. We have to compare it to the fugacity coefficient, which is given by this of a component in a mixture. So now we can summarize now the properties of the three ideal substances we have considered. One is the ideal gas, which is for the pure component. For mixture, we have looked at two different ideal substances. One is the ideal gas mixture, and another is the ideal solution. So I can summarize that in terms of the chemical potential. This would be a pure component, can be written as just from these follow just from definition, but I am now inverting them to write the chemical potential of an actual substance as a deviation from the corresponding ideal substance. And whatever is left out is given by the fugacity coefficients. Right? So I can also write this for mixture. Mixture, we have two different expressions. You see the significance of this when we do vapor liquid equilibrium. These I equal to 1 to C. So you can see here the role of the fugacity coefficient for the pure component and the fugacity coefficient of the each component, as well as the activity coefficient of each component in a mixture. What is the role? They act as corrections to some ideal substance chemical potential. So what we are saying is that the ideal gas chemical potential for each pure component, right, is given by this, but the actual chemical potential of the actual substance can be written as the ideal gas chemical potential plus a correction, which is RT times the logarithm of the fugacity coefficient of the pure component. In the same way, for each component in a mixture, the actual, this is nothing to do, I can simply compare it actually, comparing with the ideal mixture chemical potential. There are C of them. For each component I can either write, if I write it as a correction to the ideal gas mixture chemical potential of each component, then the correction will be given by RT logarithm of the fugacity coefficient of the component in the mixture. But if I want to write it as a correction from the ideal solution chemical potential, then the correction will be provided by the activity coefficient. So the fugacity of the pure component, the fugacity coefficient of a component of each component in the mixture, and the activity coefficient of each component in a mixture, right, give the corrections, right, to the actual chemical potential of either the pure component or that of the mixture, and they give the measure of the correction or deviation from some ideal substance chemical potential. This will summarize the whole definition of the ideal substance, and also how the mixture, actual substance or the actual mixture chemical potential is corrected by each one of these coefficients. Are there any questions? Yeah. No, it doesn't. It's a universal gas constant. It's a way of introducing it. It doesn't matter or not. R is still the gas constant. Compressibility factor is not defined only for gases. It's only a definition. RT is a measure of the energy. That's all. Right? Because a chemical potential has a measure of units of energy per mole. Right? So if I want to correct add something, it should have the units of energy. And RT is a standard way of introducing. It's only a definition. Right? So it has nothing to do whether all the formulas that we have seen are we restricting R comes everywhere. Not just a gas, ideal gas mixture. All real gas mixtures, real liquids and so on. Right? So that has nothing to do with the fact that it is referred to as a gas constant. It's a universal constant, that's all. Any other questions? So we know what we used before. We are now in a position to discuss multi-phase because we looked at the criterion for equilibrium. But before we do that, we need to quickly derive the phase rule for the multi-phase, multi-component mixture. We have already derived the phase rule for the pure component. So I now list out. So now we have to simply count the number of equations and the variables. Now in the case of the pure component, we consider 4 sets of variables. Any 4 sets of variables. So mainly it means there are 2 variables per phase, right? Because it is characterized only the homogeneous state. If you want to step outside that and move to heterogeneous state, have more than one phase, then I have to consider 2 variables for each and every phase. Right? Similarly, when I go to mixtures, I will now get C minus 1 plus 2, it will be C plus 1. It reduces to 2 for C equal to 1. So then I have EB. So now, without making any reference to particular sets of variables, it is clear that because phase rule only relies on counting of variables and equations, and it simply subtracts the 2 and says this is the degree of freedom. So it's a very true way of arriving at a degree of freedom. So now all I can see from here that C plus 1 variables per phase are required to characterize each phase. So the total number of variables would be pi times C plus 1 of all the phases. Now clearly the constraints of equilibrium, namely the equality of temperature, pressure and chemical potential, mean that these variables are not all independent because there are equations constraining them. Actually you have to take that into account. That leads to the whole idea of the degree of freedom. Now let's list the equations the same as in, we have to go back to how we consider the phase rule for pure component. These equations are the same, and clearly there are pi minus 1 independent equations here. Again, pi minus 1 independent equation. Now, if you look at the other remaining equation for the pure component, it was but now chemical potential of a mixture as a whole doesn't have any meaning. We have for each one of the C components, we have the equality of chemical potential among all phases. So how many equations is this? Right? It is actually pi minus 1 times C. So let's now count the equations alone. Right? They are pi minus 1 times C plus 2. So to the degree of freedom, I simply have to subtract from the number of variables the number of equations. That's all. So let's write that. So F is equal to pi times c plus 1 minus pi minus 1 times c plus 2. So it would be pi c plus 5, and then I have minus plus 2 pi minus c minus 2. So pi c and pi c would cancel. I have pi minus 2 pi, it would be minus pi and c plus 2. So f is equal to c plus 2 gives the now the choice of variables is open to, we can choose from either this or in between, or this is the most common, and this is what we will take. So the choice of variables, that's very important. Not just any set of intensive variables or as the books claim. It has to be referred to particular choices of variables. It can be in fact multitude of sets of variables can be considered, because these all have a fundamental equation behind them, behind each set of variables. That's the criteria for the choice of the set of variables. But we also pointed out that by eliminating successive mole fractions, we can also introduce new variables and new Lagrange transforms. We are not going to consider that. Common phase diagrams are plotted in terms of the temperature, pressure, and mole fractions, not in terms of the specific entropy, specific volume, or the temperature, volume, or the entropy and pressure, or any other set of variables we may consider. So now phase rule can be interpreted in saying that from among the set of these variables, what does it mean, the degree of freedom? That means that I consider first the set of variables, and the set of variables we will now list out. Many sets are possible. The most common set considered, when Gibbs himself did not consider this set, but a different set which we won't talk about now. So the set of variables are P1, P1, Z1, 1, Zc minus 1, 1. All the way then I have P2. That is for the second phase. These are the sets of variables I am considering. All the way up to P5, P5, Z1, 5. These are the sets of pi times c plus 1 variables. However, as we saw in the case of the pure component, because this is the most popular also. One reason is that the temperature and pressure are easy variables to experimentally control, and so you can plot the phase diagram in terms of those. Another reason is also probably that two of these variables, the temperature and pressure, themselves appear directly in the criterion for equilibrium. If you compare it with this, here I have to express T1 in terms of Sp and the C minus 1 mole fraction. Here that is not required, but they themselves are variables in the set. So I can now simplify and come up with what may be called as an effective set of variables. So I will now call this the common temperature of all the phases, and then reduce the number of variables. If I know that all the temperatures and pressures of the phases are the same, why should I consider more number of variables and then each time reduce it? So I can do it for once and for all, right? And have something dp. Of course, the other variables would be there, z1, 1 or 2, then go on up to z1, 5. So now what is the effective number of variables, right? The effective number of variables can be 2 plus c minus 1 times 5. So obviously number of variables has reduced, and so has the equation. The number of equations correspondingly has reduced, because now I no longer consider, because I have already made use of those equations. So those are no longer equations that I have to consider. So the equations are only these, which is phi minus 1 times c. You will see that if you subtract now, you will get the same answer. The numbers of the variables as well as the number of equations are both correspondingly decrease. Right? So if I now subtract, right, 2 plus minus this, you will see that I have a 2 by c would cancel and then I get c minus. So what I can say from the phase rule that from among the set of actually 2 plus c minus 1 pi, which is the temperature and pressure, and the c minus 1 mole fraction of each of the phases, there I cannot simplify any further because I don't have any relation among them unless I consider the equality of chemical potential. The phase rule effectively says from among the set I can independently choose c minus pi plus 2 variables can be independently chosen. From among the set of this 2 plus pi c minus pi, from among those variables, I can independently choose c minus pi plus 2. Right? So independently choose. What the phase rule also implicitly says, the rest of the variables are then uniquely determined. Because otherwise the phase rule really is not very helpful. If I can have multitude of states for my choice of variables, because my whole idea is to fix the state. Another terminology used in the book. If you want to fix the state unambiguously, how many variables I can specify independently? The phase rule gives the answer. Phase rule, you can restrict the phase rule rather than considering all possible sets of variables. You can simply consider the temperature, pressure, and the mole fraction. You say these are the variables I am going to consider every time, right? And I know how many there are. 2 plus c minus 1 times pi. The phase rule says from among these I can arbitrarily pick, right, c minus pi plus 2 variables. And then the rest of the variables are automatically determined. So I have a unique state corresponding to this choice of variables. We have to complete the phase rule in terms of the statement like that. From among the set of variables, one can independently choose c minus pi plus 2 variables. And the rest of the variables are uniquely determined. So I have a freedom to choose only c minus pi plus 2. That automatically fixes the state, which means all the other variables are determined. How am I going to determine those equations? This is the basis of all phase equilibrium calculation. You should also know the equations. I am going to calculate the remaining variables by employing these equations. So that is what is remaining, right? This I have chosen. What is remaining is the number of equations. That's what I have subtracted, right? So that many equations, as many equations are there as are variables to be determined. That is why I have the freedom to choose certain. If I leave everything open, I don't have enough equations to find all the variables. So I subtract from the whole list of variables, which are larger in number than the number of equations that I have. I can choose c minus pi plus 2. Then I have exactly the same number of equations as there are variables to be determined. Right? So I will use those equations to determine the variables so the state is fixed once and for all. Right? So we will see now how to apply the phase rule and also these equations, not only to look at representation of phase diagrams, right? How they are represented and how to verify, for instance, if the data that is given is actually consistent with the phase rule. Right? So you have to understand that that's the qualitative in terms of interpretation of phase equilibrium data. The second part is actually the calculation of the phase diagram, how to numerically, quantitatively calculate it. that is by using these equations, but we have to develop models for the chemical potential. When we look at some of those specific models that are used to calculate phase equilibrium. So that will be the main topic for the next 1 or 2 weeks at least.